we began the discussion of gravitational waves, which all occurs in what we call the weak field approximation. Weak is just that all the components of H are much less than 1 in magnitude. And in this situation, the Einstein equations, in the absence of any matter, the Einstein equations, as I showed you last time, the Einstein field equations, in the absence of any matter, just become the Ricci curvature Ricci tensor is 0, and the Ricci tensor in the weak field approximation is minus 1/2 box h mu nu, where box is eta mu nu d mu d nu in harmonic gauge. Okay, and we discussed two ways of writing harmonic gauge. One way was g mu nu gamma mu nu lambda equals 0, and this is equivalent to box of x mu or x lambda equals 0. So in this lecture, we're going to discuss these gravitational waves a little bit more and understand their two polarizations. They're very similar to electromagnetic waves in the sense they have only two independent polarizations. And then we'll discuss how they are actually spin 2. The graviton is a spin 2 particle, just like a photon is a spin 1 particle. So harmonic gauge in the weak field approximation, we already discussed this. It looks like d mu h mu nu minus 1/2 delta mu nu h lambda lambda equals 0. And sometimes this variable is defined as h bar mu nu. This is the trace reversed. H mu nu. Just take h, take off its trace, such that the trace of h bar is minus the trace of h. And this condition here means that it's transverse. Okay, the reason we say it's transverse, if the 4 divergence vanishes, is we're dealing with linear theory here, and we can just Fourier transform. And if we Fourier transform, this d mu goes to I k mu. And transverse means that whatever matrix you have here, when you contract it with the k is the 4 vector for the graviton, the 4 momentum of the graviton. It's really the 4 wave number. In quantum theory, it becomes the 4 momentum. But the 4 vector telling you the direction the gravitational wave is traveling in is k mu. And if k mu dotted into h is 0, that tells you that the orientation of these h's are perpendicular to the k vector. We'll see all this. This is all 4-dimensional, but we'll see it in much more detail in a moment. Okay, so are there any questions about this? Conceptually, it's very, very simple. We linearize the metric, we stick it in the Einstein equations, find the wave equation. And then we have to deal with all this complication of many coordinate systems, right? So the reason we had to do this is that the equations are invariant under changing coordinates from x mu to x prime mu. That's a very beautiful feature of the Einstein equations, but it's an absolute pain if you're trying to solve them, okay? Because it means if I give you a solution of them, it's not unique in any sense. I can just change coordinates, and it's another solution. So there's this huge freedom in writing down solutions. Yes?
Whenever we write box here, do we always mean the partial derivatives, or does it sometimes mean the covariant derivatives?
That's a good question. I will do what people typically do, which is what I mean is defined by the context. Okay? So you should be able to figure that out. Yeah. So, okay. So let's think what this box means. I did this expansion. I only keep this to first order. This is to first order in H. Right? That's very important. I'm doing linear theory. I drop anything quadratic. So I had an inverse metric. I just forget about it because it multiplies something already linear in H. So this box is Minkowski space box because to keep anything else would not be consistent. So this one is Minkowski. Okay, so I use eta there. However, these equations are completely general. This could be in any nonlinear gravitational field, right? I didn't say anything about weak field approximation here. This is general. And this box here is the fully covariant, the full box. So that means d nu, g mu nu, acting on x lambda. But as I explained last time, this is a bit tricky. This whole expression is a bit tricky because x is not a tensor anyway. The coordinate x isn't a tensor, right? When x changes to x prime, x alpha goes to x prime alpha. It's a function of x, but it's certainly not equal to dx prime alpha dx alpha x alpha. It's not equal to that. So x itself is not a tensor. So what the hell do I mean when I write this down? It means, as I said last time, that you're supposed to treat this as a scalar, as 4 scalars. Okay? So this is a clever little mathematical formula, but it's not consistent with the formalism. So this is sort of one of the irritating things about general relativity. The algebra is all very big and complicated, and people love to invent different notations and tricks and all that to make their lives easier, but it can be very confusing. Okay? And unfortunately, that's just the way it is. So more or less every author on general relativity picks a different convention and a different meaning and a different notation. Lots of people ask me, why are you keeping all these horrible indices? Can't we write all this down without indices? Because after all, the coordinates don't really mean anything. The coordinates are arbitrary. The indices are associated with the coordinates. And so if you look in Robert Wald's book, for example, he uses abstract index notation. Okay, now I defy you to explain in 2 sentences what that means. Okay, but basically what it's putting in the indices, but reminding yourself that they don't really mean that much. But anyway, that's what he likes to do. I'm taking the very nuts and bolts approach in this course, so very explicit and somewhat painful. Are there any other questions? Okay, so we have this equation that box h mu is 0, so immediately we see that we have 10 objects, the h mu nu, obeying the wave equation. However, these 10 objects are not free. They have to satisfy this coordinate condition as well. And on top of that, we will have a residual coordinate freedom, which is that we can change, we can perform additional coordinate transformations while preserving both this and that. And so we'll do all this explicitly now. So let us solve this. So let's call this equation 1. Let's solve 1. It's an easy equation to solve, so we write h mu nu of t and x is equal to the sum over k vectors of epsilon mu nu k e to the I k dot x plus complex conjugate. So in classical physics, it's often useful to use imaginary numbers, even though you can always avoid using imaginary numbers. You can always write things in cosines and sines, but the formulae a little bit briefer if you use an I. And then, of course, this equation satisfies 1. So we have to put the complex conjugate so the h mu nu is real. This satisfies 1 if k squared equals 0. Now this k dot x, what that means, of course, is k naught, this is minus k naught t, because k dot x is eta mu nu k mu x nu, and x nu is tx. I'm going to continue setting the speed of light equal to 1. So k dot x is minus k naught t plus k dot x. And this equation is just k naught squared equals k squared. K naught equals plus or minus k. And you can and then without loss of generality, we can choose k naught equals plus k in 2. Because we have the positive frequency on this one will have e to the minus I mod kt, and that'll have e to the plus I mod kt. And you can convince yourself that is the general solution of the equation. So here is our solution of the equation. For every vector k, we have an arbitrary amplitude. This is an amplitude and phase. Okay, so that quantity has a magnitude. For each mu and nu, epsilon has a magnitude, also has a phase. The phase determines the phase of the waves. So the phase you can think of coming into the exponent and shifting the phase of the waves in space and time. Okay, so that's the general solution representing a propagating gravitational wave. But we have to take into account the gauge fixing. We must take the gauge fixing, the gauge condition, harmonic gauge, into account, i.e., from this equation, when I Fourier transform, this d mu on h just brings down an I k mu. Okay, so that'll give us k mu epsilon, let's write it this way, k mu epsilon mu nu equals 0. Sorry, it's with this term as well. It's k mu epsilon mu nu minus 1/2 delta or eta mu nu epsilon lambda lambda equals 0. Should really think about this for all k, for all vectors k, and k naught is defined to be the positive square root. So when I write this equation down, k naught, k mu is equal to k naught, k equals k. I'll just write the magnitude of the 3 vector as k without any modulus sign. So I'm going to call this thing k. And k with downstairs indices, of course, I have to reverse the sign of the 0 component. So that has a minus k. Okay, so superficially, you have 10 numbers for every k vector, 10 complex numbers for every k vector. But here you have 4 conditions, so actually you only have 6 complex numbers for each k vector. And in a moment, we'll see we really only have 2, because we still have residual coordinate freedom. Namely, if we change coordinates from x mu to x prime mu, which is x mu plus epsilon mu of x, then box x mu equals 0, box x prime mu equals 0, as if box x box epsilon mu equals 0. So I'm still free to do coordinate transformations which are harmonic, namely the coordinate transformation satisfies the wave equation, and that will obviously preserve the gauge condition box x equals 0. We can see that explicitly so under a coordinate transformation, under a coordinate transformation, we have g mu nu prime of x prime equals dx dx prime dx dx prime g alpha beta. Okay, we if g alpha beta is eta alpha beta plus h alpha beta, and g prime mu nu is eta mu nu plus h prime mu nu, and x prime mu is x mu plus epsilon mu. This, of course, implies x mu is approximately, well, x mu equals x prime mu minus epsilon mu. This is approximately x prime mu minus epsilon mu of x prime. Okay, so this to first order in epsilon. So the idea is we've got a small metric perturbation, h is a small number, h prime is a small number. So when I do a coordinate transformation, I'm going to do a small coordinate transformation to keep h small. So I can do small coordinate transformations. And if I do coordinate transformations whose magnitude is the same order, we treat epsilon mu as the same order as h mu nu. Okay, so when you do linearized gravity, you have linearized coordinate transformations. And formally, the magnitude of epsilon is the same order as the magnitude of h, and you don't keep h squared, and likewise you don't keep epsilon squared. Okay, so I have to plug this formula for x in terms of x prime into here and keep terms to order epsilon. That's all. Okay, so now it's easy to see what happens. This equation implies that eta mu nu plus h mu nu is approximately, we're only going to keep terms to linear order in epsilon. So over here, I've got eta plus h to 0th order in epsilon. This is just dx dx prime. This gives me a delta. Okay, so to 0th order, I get eta mu nu, because I have a eta times 2 deltas. To 1st order in epsilon, I'm going to get dx dx prime. This will give me minus epsilon alpha comma mu, right, from this term. This is going to give delta beta nu, and this I just keep the eta. Okay, so, and then from this term, the dx dx prime acting on the epsilon is going to give me the same thing. Here I get the delta in this position, delta alpha mu. Then I have epsilon beta comma nu. And then I have eta alpha beta. And so this equals to, this is to order epsilon only. I drop epsilon squared. Epsilon squared would come from the product, right? Of the epsilon terms. I don't keep it. And so here all we're doing is seem to have the indices. Oh no, they look okay. So this gives me a eta nu alpha, and so this just gives me eta mu nu minus epsilon nu comma mu minus epsilon mu comma nu.
Sorry, why don't we have h mu nu term on the right hand side of the equation?
Which one?
The last equation.
This one?
Yeah.
What do you want? What extra term?
I mean, you will have a product of the chronicle delta, right? And in d mu nu, you have also h alpha beta.
Yeah. So over here, let's write that out. We have delta alpha mu plus epsilon alpha comma mu. That's the first Jacobian, right? And then the second Jacobian is delta alpha nu plus epsilon beta, beta nu.
Yes.
Okay?
Yeah.
So now let's see, and then the G, of course, gives me an eta, alpha beta.
And why don't we have plus h beta, h alpha beta in T?
Oh, the epsilon?
No.
Sorry. This term, these two, give me that one. This and that gives me this one. There's a minus here. This and that gives me this one. This and that gives me this one. And I drop epsilon squared.
That's not what I mean. I mean, when you substitute, you only substitute eta.
Here?
What about h?
Oh, yeah. Then we have, yes. To order, yes, good point. So this is to linear order. in epsilon and h. So the point is you treat epsilon and h as the same order. They're both small. So epsilon times h is h squared.
No, but you will have h times delta.
Yeah, 2 deltas.
Like,
Sorry, very good point. Yes, it should be there. Thank you very much. I just forgot it. Thank you. It should be there. So yeah, what we conclude from this is that h prime mu nu is h mu nu minus epsilon nu comma mu minus epsilon mu comma nu, right? Yeah, thanks. The h is there. Okay, anyway, it's good to discuss these things because you see that I dropped the epsilon h term, and you should drop it because you're treating h as small and you don't want to do big coordinate transformations and make your metric not a weak field metric. It should stay a weak field metric. Okay, so we've learned that by doing small coordinate transformations, I can still change my h. And so I can alter the epsilon mu nu, right? So this means that in equation 2, if I Fourier transform this equation, these mu's are just going to go into So I need to tell you, so in 2, let's see, let me push this up. We can choose epsilon mu. This is our coordinate transformation. We can express epsilon mu. You see, yeah, so we know that the epsilon mu nu, okay, if epsilon mu satisfies box epsilon mu equals 0, we remain in harmonic gauge. Okay, because box x prime is still 0. So we're still in harmonic gauge. So the same condition, that transverse trace reversed condition will still be true. But of course, now we can express epsilon in terms of solutions of the wave equation. Epsilon mu of x is equal to sum over k. And then I'll put an I in here just for convenience. E to the I k dot x plus complex conjugate. Where again, where k naught equals magnitude of k, as before. Okay, so now if I substitute this into here, I will call this equation 3. Two and 3. Substitute into 2 and 3. So I'll substitute this into equation 3. The derivatives are just going to bring down k's, and I've picked the I here to just cancel the minus sign, and what we end up with is that epsilon mu nu k prime, so the polarization tensor of the gravitational wave changes by epsilon mu nu plus k mu epsilon c nu plus k nu c mu. Okay, so whereas it looked like we had 10 complex constants in the gravitational wave, this transverse trace reversed condition gives us 4 equations, reducing it to 6. And then we still have 4 arbitrary constants to play with at every k, at every vector k. We still have these 4 constants, which we can use to change the polarization tensor of the gravitons and put it into a more convenient or canonical form. So you can check that. We can check that that this change in epsilon preserves the gauge condition epsilon k mu epsilon mu nu minus 1/2 k nu epsilon mu mu equals 0. That's our gauge condition. This equation at the bottom of the top board. And obviously, if I shift this, I'm going to get these terms. So the change is going to be given by these terms, which will be k squared is 0. Remember, so k nu will be 0, so this will be k mu c nu plus k nu c mu. And then over here, I'm going to have a change in the trace, which would be just k dot c. K nu, k mu c mu. Okay, so the change is this term, and this is 0, because k squared equals 0. And then these two terms are identical. Sorry, I've got a factor of 2 wrong. Well, there are 2 terms here. So when I take the trace, there's really a 2. Okay, so the change in the trace of epsilon is twice k dot c. 2k mu c mu. Free index is nu. So this term cancels this one. Okay, so now let us consider, just like we did in electromagnetism, let's consider a gravitational wave traveling in the z or z direction. And what that means is that k mu is k 0, 0, k. Okay, the phase of the wave is only a function of z. The wave is completely independent of x and y. The wave solution only depends on the spatial coordinate z, also depends on the time, and it will clearly be traveling at the speed of light, right? So k mu x nu eta mu nu is equal to minus k t plus k z. So that's k z minus t. So obviously the wave is moving along in the positive z direction at the speed of light. It's enough to consider such a wave because you can obtain a wave in any other direction just by rotating this wave, right? So we've chosen it to go in the z direction, but I can rotate the z direction into any other direction. And since the whole theory is linear, the most general solution is just a superposition of solutions like this. So you really lose nothing by focusing on a single wave going in the z direction. And then, of course, k mu with downstairs indices is minus k 0, 0, k. And then the gauge condition reads, so let's look at this. The gauge condition is up there. The k mu, bottom of the top board there. So k mu epsilon mu nu minus 1/2 delta mu nu epsilon lambda lambda equals 0. This reads as follows: k times epsilon 0, 0 plus epsilon 3, 0. The only components of this k, let's raise the k index and lower this one and make this an eta. So this vector only has two components in the 0 and the 3 directions. So in the 0 direction, I get k epsilon 0, 0. Then I have to sum over the, I have to include the index 3, and that gives me k times epsilon 3, 0. And then I have plus 1/2 k minus epsilon 0, 0 plus epsilon 1, 1 plus epsilon 2, 2 plus epsilon 3, 3. I'm just writing out the trace explicitly. Okay, so that's the 0 component. This is the component of the gauge condition, is 0. And then the 1 component, so this would be nu equals 0. Right, and then if nu equals 1, the equation I get is k times epsilon 0, 3 plus epsilon 3, 3. And then here I get a minus 1/2 k minus epsilon 0, 0 plus epsilon 1, 1 plus epsilon 3, 3 equals 0. And then if I look at nu equals 2, I get k epsilon 0, 1 plus epsilon 3, 1 equals 0. And nu equals 3, I get k times epsilon 0, 2 plus epsilon 3, 2 equals 0. So there are 4 equations for 10 unknowns, and that means you can eliminate 4 of these components. So it's easy to see these equations imply epsilon 0, 1 is at minus epsilon 3, 1. Epsilon 0, 2 is minus epsilon 3, 2. Epsilon 0, 3 is minus 1/2. Epsilon 0, 0 plus epsilon 3, 3. And epsilon 2, 2 is minus epsilon 1, 1. Okay, where did I get those equations? Obviously, the first 2 are just these. And then the other equations I get by adding and subtracting these equations here. if I subtract them, obviously I'm going to cancel the epsilon 3, 0. I'm going to get epsilon 0, 0 minus epsilon 3, 3. Everything will go here except the epsilon 0, 0 term. And we'll end up with so I guess the third equation I get by adding these. Yeah, this all goes, and so I add these. And then the last equation I get by subtracting them. And subtracting them and then using that equation. And I'll get that the sum of the epsilon 1, 1 and epsilon 2, 2 have to be 0. Okay, so there are these four components we've expressed in terms of these components. So we've eliminated 4. So we have eliminated 4 components in terms of the others, of the other 6. And then we still have the residual coordinate freedom. Epsilon prime mu is equal to epsilon mu nu plus k mu c nu plus k nu c mu, where I can pick the c however I like. So we still have this residual coordinate freedom. And if we write that out, we see epsilon 0, 0 prime is epsilon 0, 0 minus 2k c0. Okay, that's just using the fact that k with 0 downstairs is minus k. And epsilon 1, 3 prime is epsilon 1, 3 plus k c1. Epsilon 2, 3 prime is epsilon 2, 3 plus k c2. Epsilon 3, 3 prime is epsilon 3, 3 plus 2k c3. And so now, obviously, we can choose these c's as we like, and so we can choose the c, can choose this vector c to set epsilon 0, 0 prime equals epsilon 1, 3 prime equals epsilon 2, 3 prime equals epsilon 3, 3 prime equals 0. And then we have that epsilon mu nu, viewed as a 4 by 4 matrix, is 0 everywhere. Except in the transverse components. Okay, so this is now transverse and traceless. Okay, so in sort of elementary treatments of gravitational waves, you'll see people just go straight to this formula and say a gravitational wave is transverse and traceless. But I hope in going through the whole rigmarole of fixing the coordinate condition and exploiting the residual coordinate freedom, you'll see how we assure ourselves that we can always we have shown you can always put the gravitational wave into this form. Can always put a linearized means just keeping order h, gravitational wave in this form. just to be more, can always express a linearized gravitational as a superposition of such waves. Okay, so instead of 10 complex numbers, epsilon mu nu, we only have 2. And we therefore say gravitational waves have 2 independent polarizations. Okay, are there any questions? So everything I've done you can do for electromagnetism in just the same way. You just do a gauge transformation of the A mu by some vector that you pick Lorentz gauge, you do all this, and you can show that the A mu can also be chosen. So in EM, in electromagnetism, we can always put the vector potential into this form 0, 0, if it's going in the z direction, epsilon 1, epsilon 2. Okay, where epsilon 1 and epsilon 2 are 2 arbitrary complex numbers. So we say there are 2 polarizations, one of them in the y direction and one in the x direction, if the wave is traveling in the z direction. Now, what about the spin of the graviton? And I'm using the words graviton, though everything we're doing is really classical. But we want to know what the spin is. So can anyone tell me what spin is? What is the definition of spin in physics? What's the spin of a particle? Actually, I have to tell you a funny story. I went to, in my position, I frequently have to go and speak to government and explain to them why what we do is valuable and why you're all valuable, and why they should support you. And in Canada, it's kind of interesting. The civil servants here are quite different, at least. I mean, my only comparable experience is in the UK, where people are rather cynical. But in Canada, they actually listen, okay? And so as we left one of these big meetings about finance and all that, one of the civil servants, we're going into an elevator, and he says to me, by the way, I've got this really, I was telling him all about, where physics is now and what are the exciting prospects and all that. He said, you know, there's some question that really bothers me. What is spin? And I had to, it literally was going into an elevator, so I had to give him an answer in 30 seconds, okay? So I said, it's a little hard for me to explain, but I promise you I will send you something about it. So I did, and what I did is I sent him a book. Okay, so tell me, which book would you send someone if you wanted them, you know, who's not a physicist, if you want them to understand what spin is? He's a very smart person, very, you know, educated person, just not a technical physicist. What would you do?
Alice in Wonderland?
No. No, that would just be jokey. It's not a joke. He seriously wants to know what the hell is a spin. You know, when people talk about quantum computers, it's all about these spins and how they interact, and there's entanglement, and blah, blah, blah. He says, what on earth is a spin? Right? So the book I sent him was Roger Penrose's book, The Road to Reality. And if you look in there, okay, chapter 35 or something, it's an absolutely beautiful explanation of spin. Okay? I encourage all of you to read it too. He didn't ask me any more questions. Okay. But where does spin come from? What would you say is the most fundamental feature of spin? What does the spin of a particle tell you?
How it rotates?
Yes, it almost. It's not so much how it rotates.
But how it transforms under rotation.
Excellent. Yeah. Spin is to do with transformation under the rotation group. The rotation group is a part of the Lorentz group. Okay? So the Lorentz group is a symmetry group of all of physics. And that's telling you that physical states, like the states of a particle, must transform in some way under the action of rotations. And that means they form a representation of the rotation group. Okay, so how many of you have done any group theory? You've all done group theory. Oh, you did that here? Excellent. Fine. So the spin is a very, very abstract thing. It's basically saying if I take the world and I rotate it, every particle's state is going to change in some way. And the way it changes is according to what representation of the group it is in. Okay, so, I mean, it's just amazing that we can state that in complete generality. So what is the spin of a graviton? Well, the way I determine its spin is by doing a rotation of it. All right, so I need to take this polarization tensor and rotate it, and that should tell me what spin the graviton has. Okay? So graviton, I put it going in the z direction. Let's imagine it's going in any direction. This is my k mu vector. The graviton's going in some direction. The wave is transverse. After we've done all this gauge fixing and gauge transforming, the interesting parts of the graviton are all transverse to the k vector, right? And so I want to do rotations which leave the momentum of the graviton unchanged, right? Because you can see that every wave, in fact, yeah, I should really draw this as the 3 vector. Let's think in 3 dimensions. It's just 3 dimensions. The wave is going in some particular direction. The energy is, of course, just equal to mod k. So there's really a vector in 3 dimensions. And then the polarization of the gravitational wave is transverse. It's in the, if k is in the 3 direction, this is just the 1, 2 directions. But in general, it looks like this. This is the polarization. I want to do rotations on this, but I don't want to change the k vector, right? Because the k vector is going in some particular way, and the waves for each k are independent of each other. So I can just fix the k. I can still do rotations which leave k fixed. So what is that group? Okay, are there any rotations I can do which leave the direction unchanged? What are they? Rotations around k, right? I can do rotations around k. This is called the little group. Okay, the language was introduced by Wigner, who was probably the leader of introducing group theory into physics. And he called the little group the group that leaves the wave number or momentum of a particle unchanged. What is the group?
SO2.
It's actually, yes, SO2. Right, just 2 by 2 matrices, 2 by 2 rotations around that vector. So in our case, we have, in our case, the k vector is going in the 3 direction, let's say, and so the SO2 is just acting in the xy plane. Okay, so the transformation would be that epsilon prime ij is equal to O I L O J M epsilon J M. And then, as usual, we can rewrite this as epsilon prime equals, this is LM. Epsilon prime is O epsilon O transpose as matrices. I have to put the transpose in here because this is not a regular matrix multiplication, right? I'm multiplying the column by the column. Okay, so we do it that way. And if you want to think about it as matrices, we're only in the xy. It looks like this: 1, 2 prime, epsilon 1. This is epsilon 1, 2 prime. This is minus epsilon 1, 1 prime is equal to, and we just have our usual rotations, sine theta. So in our case, the rotations, the little group equals rotations about the z-axis, and they just rotate x into y, and they don't do anything to z. So sine theta, cos theta. And then we have epsilon 1, 1, epsilon 1, 2, minus epsilon 1, 2, minus epsilon 1, 1. And then we have a rotation matrix again. Cos theta, sine theta. I want the transpose this time. Sine theta, cos theta. Okay, so that is how the epsilons transform. And notice they transform. You can work all this out. I won't bother, but you can work it all out. And notice that it transforms as the square of some trig function, right? Whereas a vector transforms as cosine theta or sine theta. A 2-index object obviously has 2 rotation matrices, so it goes as the square. And then there is a very nice trick from group theory. So there's a theorem in group theory that any abelian group, abelian means that all the elements commute, any abelian group has only one-dimensional irreducible representations. So if you're ever considering some group which is abelian, you can always express its representations in terms of one-dimensional, as a sum of one-dimensional representations. So somehow this has got to be a one-dimensional. So the group is SO2 is abelian. So all its irreps are one-dimensional. Okay, one-dimensional representation of a group is just the group acts on something by a phase. That's all. One by one complex unitary matrix is just a phase. And so you can check the following, that epsilon right is epsilon 1, 1 minus I epsilon 2, 2. And usually we define this as epsilon plus minus I epsilon cross. Epsilon left, which is epsilon, just the complex conjugate, epsilon plus I epsilon x. These transform to I theta epsilon right and epsilon left at minus 2I theta epsilon left. Okay, where the theta is just this angle. Okay, so it's obvious you get things like cos 2 theta and sine 2 theta when you multiply all this out. You're guaranteed by group theory that if you pick the right combinations, they will only transform into themselves. So then you play around with linear combinations of these two things until you find this transformation law. And this means spin 2. If something transforms under rotation with twice the phase of a vector, you say it has spin 2. Likewise for a mu, for E and M, we get our epsilon 1 and epsilon 2, which I told you about before. And in that case, you have something much simpler, that epsilon 1, epsilon 2 would be primed, would be O times epsilon 1, epsilon 2. And in this case, you can take linear combinations. Epsilon plus is epsilon 1 minus I epsilon 2, and epsilon minus is epsilon 1 plus I epsilon 2. And this leads to epsilon plus prime is e to the I theta epsilon plus, and epsilon minus prime is e to the minus I theta epsilon minus, and these are, the photon is spin 1. So even in the classical theory, it's useful to know how things transform under rotations. Group theory is still useful in the classical theory. Spin is not quantized. There's no physical quantity corresponding to the spin. There's no h bar. It's only when we go to quantum theory that angular momentum is quantized. But nevertheless, the spin is still meaningful in the classical theory, and it just tells you how the different modes transform under rotations. Now, yes, go ahead.
Seeing your definition of epsilon right and left, should it depend on like epsilon 1, 2 at all?
Sorry. Let me. Oh, sorry, I just wrote it down wrong. I'm sorry. There's no 2, 2. 1, 2. When I wrote it down, I eliminated epsilon 2, 2 in terms of epsilon 1, 1. Sorry, that was just a typo. Thank you. Any other questions? Yeah.
Is there also a typo in the matrix up there with the E21, which would be E12?
Here? They're identical. Okay, so it is identical.
Okay.
So epsilon is always symmetric, so that's identical. Any other questions, typos? Mm-hmm.
Why is everyone convinced the graviton exists?
Yeah.
I
Well,
I'm thinking that space-time is quantized. That doesn't make sense to me.
the short answer is that no one knows how to couple a classical system to a quantum system. Just doesn't make any sense to have the world half quantum, half classical. Makes no sense. So you can't go halfway with quantization. Okay, if you're studying a quantum system, you get superposition and all of this. It has to be there in quantum mechanics. When you couple it to classical mechanics does not have superposition at all. And so you very quickly run into contradictions. So actually, for this reason, this is a very, very fundamental point. And this totally relates to all my research recently. It makes no sense to treat the universe as classical and to have quantum stuff in the universe. And this is actually the origin of the multiverse theory. I mean, in my view, it's just an error. Coming about by thinking about the universe as having different classical states within which strings propagate or waves propagate. That actually makes no sense at all. And so I believe lots of people have slipped into this mistake. So we just proved a theorem, which is on the web, that, for example, the no boundary proposal of Stephen Hawking is incorrect. And this is essentially the heart of the proof. It's you can't treat the background universe as classical. It's got to be quantum. It's all or nothing quantization. Especially in GR. I mean, you can't, if you believe in the graviton, you've got to quantize the whole universe. You can't quantize the fluctuations and leave the background as being classical. That makes no sense. But that's exactly what perturbative string theory does. It takes a fixed classical background and it considers fluctuations which you quantize. Conceptually, I don't think that makes any sense. So when you start to quantize the universe, you discover all kinds of strange things. And our work is very much a beginning of that. I've got a lot of people here work on quantum gravity, but this very elementary question is one that a lot of people overlooked. Yeah, so good question. Why do we believe in the graviton? I mean, until 2 years ago, people were not even completely convinced about gravitational waves. Classical, right? I mean, the first evidence, I'll discuss the evidence for gravitational waves. That came about in, when was that? Around 1990, a binary pulsar. Sorry? The what? Hulse-Taylor, yes, exactly. So, in fact, I was at Princeton when Taylor was a faculty member there, when Joe Taylor was on the faculty, won the Nobel Prize for that work. And we were having some champagne in the quad to celebrate. And a very famous theoretical physicist, who I shall not name, came up to me and said, "What's all the fuss about? You know, he's confirmed gravitational waves exist." That's trivial, okay? The whole point is to show the graviton exists. This is not even quantum gravity. Why are they giving him a prize? And I was just like, what? What planet are you living on? So it's a funny thing, you know, that many theorists live in this funny world where they only think about gravitons, and for many theorists, like a gravitational wave was so obvious, how could it not exist? But for more, let's say, balanced people, you know, it was an open question. This was an experiment. This was a definite prediction Einstein had made, and it needed to be tested. Of course, the bizarre theorists, you know, turned out to be right. Yes, they are there. They're obviously there. They have to be there. So sometimes that works. Sometimes theoretical prejudice is correct. Sometimes it's not. But in that case, it was correct. So, okay, so classical gravitational waves are a direct consequence of the Einstein equations, unavoidable consequence. All of their properties are just predicted. There's no free parameters in anything. It's not an adjustable theory in any way. They have to travel at the speed of light. It's built into the theory. The question, you know, your question is, should you quantize them? Do they come in packets of energy like photons? It's the energy in a graviton given by h bar nu, or h nu. And the short answer is that that seems to be unavoidable. We know of no way to quantize half of nature without quantizing all of it. In fact, I highly recommend a book by Richard Feynman. So it's called something like Lectures on Gravitation. I believe it's in the library. These were some lectures he gave in Caltech in the early 60s, and somebody took notes, but they weren't published until 10 years ago or so. And so they're sort of reconstituted lectures. And he was working on quantum gravity, and he gives a very nice argument as to why gravity has to be quantized. He basically, you see, if gravity wasn't quantized, and you did the double slit experiment in quantum mechanics, you could just use the gravitational field to see which slit the particle went through. You just sit there and you measure the gravitational field of the particle going through the slits. And if gravity is classical, well, you can measure which slit it went through without without disrupting quantum mechanics. And that violates the uncertainty relations and so on. So you very quickly get into inconsistencies if gravity is not quantized along with everything else. Okay, so I think I wanted to just tell you a little bit more about gravitational radiation. And then tomorrow we will start discussing black holes. So in fact, I wanted to tell you a little bit about pulsars. And I'll keep this short. So where are we now? Spin 2. Let us put that up. So gravitational radiation is the emission of gravitational waves from some object. And in electromagnetism, we get d mu f mu nu equals minus j nu. Okay, j nu are the electromagnetic currents. Now we can go to Lorentz gauge, and this is in Lorentz. This is just d squared a nu, or box a nu. And so this leads to the radiation. So a time varying j nu leads to the emission of electromagnetic waves. Okay, so direct consequence of Maxwell's theory, not fully appreciated until Hertz. Hertz realized that Maxwell's equations imply that if you wiggle around some electric charges, you're going to get waves emitted. And the way they did that was by making sparks in the laboratory. A spark is just a place where an electric charge is moving rapidly across a gap that emits radio waves. And so Hertz produced and detected radio waves. And that was all a direct consequence of Maxwell's theory of prediction. There should be such waves, and they should be detectable. So gravitational waves, it's exactly the same thing. So in GR, we need to go back to the full Einstein's equations with the stress energy source and now study how, as this source changes, how does it emit these waves, these traveling gravitational waves. So in GR, we have Einstein's equation. And we have to keep this guy, because this guy is the source of gravitational waves. Now, it's convenient to rewrite that equation, just like we did when t was 0. You can rewrite this equation just by taking the trace, which means multiplying with g mu nu. And so this equation becomes r. The first term is just r. G mu nu downstairs with g mu nu upstairs gives you 4, right? Because g mu nu g nu alpha is delta mu alpha. So a sum over mu and alpha, there are 4 ones. So g mu nu g mu nu equals 4. So I get a factor of 4 here. 4 over 2 is 2. So I get minus 2r equals 8 pi g t mu mu, the trace of t. And so this tells me that r is equal to minus 8 pi g t mu mu. The Ricci scalar is minus 8 pi g t mu mu. So I can just take this term over to the right-hand side and rewrite this as r mu nu equals 8 pi g t mu nu minus 1/2 g mu nu t lambda lambda. It's just a rewriting of the Einstein equations, which is convenient because it leaves us with only r on the left-hand side. And then we know that this is minus box h mu nu in transverse trace reversed gauge. Okay, so obviously these equations look very similar to these equations. There's some source here. This is the source. And this is the radiation. And so this is the source for gravitational waves. And this is the radiation. So using a Green's function, we can use all of the technology from electromagnetism to solve this equation. It's a little bit more tricky because the gauge condition is a bit different. And yeah, I explained a little bit about that. So we end up with this leads you to an h mu nu, which is minus 4g integral d3 x prime mod x minus x prime. You might remember these Green's functions from electromagnetism. T minus x prime x prime. Okay, so here we assume we have some, actually this is, yes, let me write it this way. Let's call this S mu nu. The source is T mu nu minus this quantity. And so let me write this as S mu nu. T minus mod x minus x prime x prime. So we imagine we've got some stress energy tensor, which is just given. And that stress energy tensor will obey the usual conservation law, d mu t mu nu equals 0. it's a function of space and time, and I use it to build up the source S, and from that I get my my metric perturbation at time t and position x. This quantity here is called a retarded time. Yeah, so this is the solution representing the fact that if I have a source which changes, it emits a gravitational wave. And so if I draw a picture of this, here's my source. It depends on x prime. Okay, and I have to integrate over x prime to get the gravitational wave. If I'm now sitting at x, then the wave I get at time t, coming from the position x prime, this distance here is obviously modulus x minus x prime. And so the wave falls off inversely linearly with distance from the source. Then the wave I receive at time t at position x is directly given by the source evaluated at an earlier time, right? Because the source jiggles around at some time, and then it takes this amount of time for that jiggling to reach me. Okay, so that's the retarded solution of the radiation equation. So I think in view of time, I'm not going to go through any of the details. They are in the printed notes if you are interested in reading about them. And I'll just tell you the final result. The power radiated by a source by a time varying source is, so that power is energy per unit time, is Newton's constant over 45 times Q KL with 3 dots, Q KL with 3 dots, over C to the 5th, where QKL is integral d3x of 3x prime k x prime L minus delta KL x prime squared times the density of Tx prime. And the density is given by T naught naught. Okay, so this is called the quadrupole moment. And so the power radiated from a gravitational, from some matter source, is given by calculating the quadrupole moment. Q triple dot KL is equal to the third derivative, d3 by dt cubed of QKL. And this, the square of the quadrupole moment, square of the third derivative of the quadrupole moment, gives you the total power radiated per unit time. This is called the Landau-Lifshitz formula. And this was confirmed for the binary pulsar in the 1990s. So a little picture of it. The binary pulsar consists of two very compact objects orbiting each other. And so it has a quadrupole moment. And the quadrupole moment is changing because these things are orbiting each other. And then this gives off gravitational waves. As a consequence, it loses energy. As it loses energy, these two objects spiral in towards each other very, very slowly. And the spiraling in is what was observed. So the spiraling in actually causes a change in the period of the orbit. So the period gets faster, the period gets shorter as they spiral in. And that's what was observed, because these pulsars emit radio waves, and you can measure the period by observing these radio waves. So that's what Hulson-Taylor won the Nobel Prize for, is finding that this formula fits the speed up of the binary pulsar perfectly. And the error is, the observational error is now better than 1%. I think a lot better than 1%. So that was the first direct confirmation of first confirmation of gravitational waves. It's using, the emission, not the detection of gravitational waves. The first direct detection of gravitational waves was, of course, 2 years ago by the LIGO experiment. The derivation of this formula is long and complicated. It is in the notes. At some point, if you feel like it, I'm sure you can go through those. But I'm not going to do it in class, because I want to get on to black holes. Any questions about gravitational waves? Yeah.
Express h mu nu, you have this s mu nu, but s mu nu depends also on g mu nu. So
yeah, good point. Yeah, good point. So what we do here is we're working in the linearized approximation throughout. Okay, so here I can replace this s mu nu by t mu nu minus 1/2 eta mu nu t lambda lambda. And we're going to treat t mu nu as if it is in Minkowski. Okay, so what we want to do is keep, so in other words, h is of order Newton's constant times t. This quantity, there's a c squared. I've probably left out a c squared somewhere here. Yeah, this was all in units where c equals 1. H is of order this. This is t. Yes, there's some length here. You see here I've got a length squared. This is a length squared because d3x over mod x. This quantity is dimensionless. And we assume it is much less than 1. Okay, so the small parameter involved is really Newton's constant. Okay, so if you, I don't know if all of you are familiar with this, but if we go to natural units, have you done natural units? Not sure. Somewhat. So natural units, you set everything to 1. I'm sure you know that. Okay. So when you set everything to 1, g is 1 over m Planck squared. Okay. What is stress energy? It's an energy density. So rho is some mass to the 4th. Right? Mass and energy are the same. So rho is mass to the 4th. What is this length? Well, so this combination here is 1 over m Planck squared, mass to the 4th, times length squared. M Planck is a very big number. Right? M Planck is 10 to the 19 GeV. What's the density of a neutron star in natural units? You should be able to. Okay, learn natural units. They're very useful. Then you don't have to remember anything. What's a neutron star made of? Trick question. Neutron stars made of Newton. No, it's made of neutrons. How dense is a neutron star? 1 neutron in the size of a neutron, right? That's just close packed neutrons, right? It's a big atomic nucleus. That's all a neutron star is. So what's the density? Now, in natural units, the scale is the mass of the proton, roughly the mass of a neutron. So that's the scale. That's the length scale. Length scale is the size of a proton. What's the density of a neutron star? It's 1 in natural units, just made out of protons or neutrons. Okay, so the density is 1. For a neutron star is 1. Yeah. What's the size of a neutron star? You know, roughly. How big do you think a neutron star can be? Yeah, we could estimate it. We'd go through a whole lot of estimates to get it. It's a kilometer. Okay, a neutron star is about a kilometer. You can plug the numbers in here, figure out a kilometer in units of the size of a proton, and you'll figure out that this is small. The h on this, actually I told you this already, didn't I? I told you that h was 0.1. You remember it? I told you what h is. That's the h on the surface of the neutron star. It was 0.1. Now it falls off like, yeah, in fact, I wrote this down wrong because really this guy would be the size of the source. So this should be L cubed, and r is the distance we are from the source, right? So I should have written it like this. So you see why. So here I've got a huge number. That's how far I am from the source. Here I've got another big number, the size of the source, which is like a kilometer. In fact, it'll be bigger than that because it's really this size. And these binary pulsars are not directly on top of each other. So there's some factor there. Yeah, this number is very huge. And so if you put all these numbers in, you'll find the h is very small. So that's how you estimate the size of h's. Of course, the big excitement, and I encourage you to work this out before October the 15th, yourself, okay? Because LIGO has seen this. LIGO has just seen the fact that you have a neutron star with another neutron star merging, right? And you can predict the h they're going to detect from these arguments. And I'll tell you the distance. The distance for this neutron star is 50 megaparsecs, allegedly. So that's what the r is. Okay, so just plug the numbers in and you see what the h is, and you see, can LIGO detect that h? LIGO can go down to about 10 to the minus 21. Right, so it is, it's small because of this and because of that. So we're a long way away from the source. But you should be able to estimate it before it's announced. Of course, the easy way to estimate it is just to say LIGO can estimate 10 to the minus 21, and that's what it will be. But you can understand it in terms of fundamental physics by doing this. Any other questions? No? So, yes?
Does this mean that whenever people do research in GR, they always deal with linearized gravity? They never think about...
No, not at all. So...
here are results have
no.
depend on the fact that it's linear.
Here it's all linear. So as late as about 1995, I can remember going to a conference where, in fact, Robert Wald, who wrote the famous textbook on GR, he was giving a lecture about trying to justify the linearized approximation mathematically. And it's pretty fishy. Okay, the whole thing is it's really fishy. So mathematical physicists didn't even believe this formula. They said it's a nonlinear theory, you keep making these approximations and assumptions, and you're dropping terms and blah, blah, blah. So we doubt the whole thing, right? And so he gave this talk explaining, a little bit of progress in trying to prove the quadrupole formula. And I went up to him afterwards. I said, "Are you serious? You don't believe this formula?" He said, "No, actually, I'm sure it's fine. But I'm giving a talk to mathematically inclined people." So I wanted to make the topic interesting. So I gave the impression that it's in doubt. Okay, but actually, it's not really in doubt. So it's a bit of a funny subject like that. It's a nonlinear theory, very hard to prove anything, but physicists have all these kind of half-baked approximations which, seem to work. It's a bit like quantum field theory. You ask a mathematician, does quantum field theory make any sense at all? Any good mathematician will say no. Okay. Of course, quantum field theory is much worse than GR. But GR, sort of only has to be dealt with in approximations. Since that time, things changed quite a bit. And what actually changed was Franz Pretorius, who was in Canada at Alberta. Do you know him?
Yeah.
Okay. So him, yes.
Numerical relativity.
Yeah. So I'm very proud of Franz because he's South African. That's where I come from. That's why he and other people, including Louis Lehner and others, developed numerical codes to solve the nonlinear equations fully. Now, the fascinating thing is that all depends on picking a gauge. You can't solve the equations unless you pick a gauge. Guess which gauge finally worked? You already know it. You only know one gauge. There's only one answer, right? Harmonic gauge. Okay. So it's a very funny story because all the real numerical experts were picking all kinds of fancy gauge. They didn't like harmonic gauge. It's too nuts and bolts. It's like, you're going to use this connection that's not even geometrical. It's some totally ad hoc. It's really ugly. It's got all these indices. So nobody would use harmonic gauge. So Franz Pretorius was one of these people trying to get the equations to converge on a computer, and harmonic gauge worked. So it's kind of ironic. So now we have a lot of people, there's a whole industry of people solving the equations on a computer. Very, very hard to prove anything. Numerical results are always open to question. But that's the current state of the field. Some people have proven theorems about the existence of solutions and so on, but generally those are quite a long way from the realistic case. It's a very active area of research. Yeah.
What's better, numerical solutions of nonlinear equations or hand-wavy analytical arguments for nonlinear equations?
They're just different, and you need both.
Okay.
You need both. They give different insights. Hand-waving arguments would never... So, LIGO will probably win the Nobel Prize this year. The reason is that the computations are reliable now. They predicted the waveform which LIGO should see, and LIGO saw exactly the right waveform. Okay? And the rough approximations people had developed got aspects of this waveform right, but not the whole thing. Pretorius and others and Lehner and others get the whole waveform correct using a computer, and then LIGO see that in the experiment. So you need both. But you wouldn't believe the computer simulations unless you had the hand-waving arguments as well to check they make sense. Very easy to get garbage out of a computer. So, yeah, it's a very, 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 very exciting field. And by the way, Ray Weiss from LIGO is giving the colloquium here on November 30th. I think I already advertised that. Don't go anywhere on November the 30th. I guarantee it'll be fun. Okay, you need a break, and I'll see you tomorrow. We'll do black holes.